In our earlier class, we were discussing reactions of ketenes, where we said that your ketene can react with your alkene to form a cycloproduct. Same way we said your ketene can react with your carbonyl system to give you a beta lactone, and ketene can react with your imine to give you beta lactams. Okay. So, what we will do in this class, we will take individual reactions and study in detail. Okay. So, first we will see ketene plus alkene reactions. Okay. How this ketene plus alkene, ketenes, alkenes are. How they are going to react. So, that we will study today. So, what we said is that if you take a ketene, okay, and with your alkene, and what happens is that if you just thermally activate this, what you think? You think that this by rule this should go by pi 2 s plus pi 2 a, very good, and you will get your nice cyclic ketones. Fine. So, this is your reaction ketene plus alkene, like it is pi 2 s plus pi 2 a, one undergoes a suprafacial, another will be intrafacial mode. That this is on just eating your ketene and alkene. Now, we will do what happens, this reactions become really interesting if you talk about E olefins and Z olefin. If you take E olefin, the chemistry works in different way, and if you take Z olefin, the chemistry will be little bit different. They are more interesting. Okay. So, we will see how it works. If you take E olefin, how it works, and if you take Z olefin, how this whole chemistry goes about. For example, I take an ketene. You know how to now synthesize ketene. Okay. So, I do not want, because I have given methods by which you can synthesize. We discussed how to synthesize ketenes. Okay. See, if I have taken Z olefin, just I am taking a Z olefin. Okay. And if we see this chemistry, the product will be interesting. One way of writing is that see this, you get this type of product. Okay. And this reaction is very fast. But in Z olefin, but in other case, if I take the same chemistry, with an E olefin, I get one product similar to the earlier one, but I also get say I get these two products. I get this two when I do this reaction. If I have like ketene with my E type, okay, so I get these two products. But if it is Z, but this reaction happens little bit slow. This reaction goes fast. This reaction happens little bit slow. So, how to understand this? Why in case of E we get these two type of products, but in Z we get only one. Okay. a sort of, it tells you that since we get this 2, it tells you that it should be some not a concerted type of process, it should be some stepwise type of reaction, this with respect to E. Okay. And there are many studies, theoretical studies, which are saying that it is not going to a transition state, it is more like a type of intermediate. Okay. So, what happens exactly then? So, is that if I take my ketene, my methyl system, ketene here. Okay. So, I have my E olefin. So, how they can interact, because we studied that the way it interacts in ketene. No? So, this is your O minus, and here only you are connected your olefin methyl type of an intermediate. Okay. Methyl hydrogen. I have this type of system. If you think about that, it goes by stepwise mechanism, then it should be something like this. Now, what it can do? Yeah, it can nicely undergo rotation. Because of this, they have a minimum steric interaction, but they can undergo nice rotations. If they undergo rotation, you can get like this. So, I can get hydrogen this side and my methyl another way around. Fine. So, you can have this happening. Okay. So, this will give me then my consent product, right. If I this way it is, then my product should be that is why even the reaction becomes slow. Okay. Very interesting part. This is very interesting part to observe, because it happens in E olefin. So, in the case of Z olefin, what happens? Even if it rotates, it is more or less same. So, low. So, here you can see nice difference, and this somewhat says that reaction goes stepwise mechanism, and and many other studies have been done, like more theoretical, and it's to be said that it moves towards more like a stepwise than the concerted type of mechanism. That is why even reaction goes slow in case of E than your Z. Okay. That is one interesting part in this, in ketene cycloaddition. When you take your Z olefin, the reaction gives you one product, that is very stereospecific, but if you take E olefin, you get both your products. Might be the it's things to be the reaction goes through stepwise mechanism. Okay. Now, we will see some other examples, which are very nice examples of your cycloaddition. For example, I have this CCl. Okay, I take with my carbonyl and Cl. Now, what I have to do to generate my ketene? I have your substrate, I want you to generate ketene. What you have to do? Can you, based on your substrate, can you think what reagent I should add to generate ketene? It is an acyl chloride with your chloride alpha chloro. So, what you have to use? It's, yeah, if you use your zinc, okay, then you end up with a nice type of ketene. Okay. Most of the time, you know, ketene you generate in situ, right. So, you have your, if you take your cyclopentene system inside there, okay, they can react nicely, and you know that this goes by heating itself. So, does not need light. So, it is a pi 2 S plus pi 2 A and heating. So, you end up with a nice stereogenic center here, okay, with your chlorides. Fine. So, you get this type of nice product when you do your ketene chemistry. Okay. Another good way of, another example we will see how we can write for alkene, because it is very nice that generating ketene and adding with your alkene systems, you get type of very good cycloketones. Okay. Only idea is that you should remember that you are generating ketene. Okay. Otherwise, once you know that it generates ketene, then you can do the chemistry nicely. This is a very good example to understand. See, I take this substrate, okay. I add it in triethylamine. So, what do you think? Yeah, so you will get a nice ketene here. So, how to write it in a nicer way. Okay, you get a system. Just I am writing it in a way that you are going to do 2 plus 2 cycloaddition, because others are same, just you are generating a ketene, because you have a triethylamine and it is an acyl chloride type of system. So, it can pick up your thing to remove your chloride to generate your ketene and you get a system. So, I just written in such a way that I can do this cycloaddition. Okay. So, now it can eating, this can undergoes nice pi 2 plus pi 2 a cycloaddition because of that geometry nature. So, you will get a so you get a nice product like this. Because it is just a addition towards this. Okay. So, you get a nice product like this. This is these are some examples on your ketene with your alkene systems. Okay, you can. So, best remember that E and Z olefins, they are very interesting. Okay, because like Z, you can even think about E olefin doing stepwise mechanism, giving some products, two products, plus you have some examples on this. Okay. Now, we will get into the another reaction, which is like ketene plus your imine systems, very important. Okay. What you call them, ketene plus imine reactions. You can call them this Strondinger reactions, right? Most of this you call them as ketene plus imine, the famous your Strondinger reaction, to give you beta lactams. So, we will take one example, try to understand them. You have a ketene plus I can take an imine. Okay. In this case also you have your EZ imines. So, we will take first initially we will take an imine. Okay. So, you will get a nice beta lactam. I will teach you how to do the stereochemistry, but just you get this product. Okay, by unheating. Okay, you can think about other way around also. Like yeah, you can get your other way around product is so you have two hydrogens there. Now you can have your two alkyls. Okay. So, this is what olefin we are talking about. This is your E, right? E means okay. So, it is an E. See, if you most of this case, if you take your E type of chemistry, you end up with these two products. How it happens? That will be interesting to see how it happens, how you get these two products. Okay. But the basically it is a reaction between your ketene and imine to give you a beta lactam. This part, and you can get your this reaction to give you a beta lactam, but you get two products. Okay, we will see how we can rationalize that. So, I can take an ketene. Okay, can take an imine. For example, I think like I write a sort of intermediate for this process. Okay. One way of writing is that I can write it in R H, because I am doing this addition. Okay. So, I will have my C O minus, this can be dotted, but just for okay, this should be dotted one. Okay. I can have my R hydrogen and I can have my R. Okay. This is single bond. you can think like now you have studied that in systems like what happens you can do a con rotatory and dis rotatory for the closure of systems, right, that we have studied electrocyclic reactions. You can study of that like butadiene, they can do a con rotatory like that system. So if I put an axis across this, okay, and same way I can write one more way of writing. I can write it that it forms an R H C O minus N plus R then I will have my system with a double one hydrogen. Okay, just for our thinking R. Now I can have my axis here. Like your cyclobutadiene which you are thinking about, like now I can do a con rotatory. Okay, if I do a con rotatory, I can do this way, right, one. So this also in the same way, right, both, or I can do other way across, right. So the one way I can both clockwise, otherwise I can do both counterclockwise, both are con rotatory, and that is why you end up in two different products. Okay, clear. So what product you get here, if you want to draw properly, you might end up with, if you rotate this, my carbonyl, and you have your R hydrogen out, and you have your R or R. Okay, you get this product. This, if you think about this way, then you are end up carbonyl NR, then you have an hydrogen, right. So other way around, yeah, fine. So it's nice, right. So you are both, you are doing con rotatory, you gets one you getting away. So that's the two ways you can think about writing this product, and it comes nicely. So one thing you can always think in this type of reaction is that now you have a because based on your con rotatory, okay, you have a control across this reaction, because now if it say it's 50-50 these two products, can you make it 98-2? Can you make this reaction, though I want one product 98, another to be 2, can you make that? You can make it because it's con rotatory. So you can favor one side of rotation by using different substituent. If you can change the substituents and you favor only one rotation, okay, you allow this rotation only, you don't allow this rotation happening counterclockwise, you allow, so that you place the substituents like that, then you can end up with 98-2. Okay, that control you get. Fine. So another reaction, even you can see the same observation with Z imine also. Okay, we talked with E. Okay, you can even do the same chemistry with Z. For example, like I have a taking a type of conformationally locked type of system, like it's a Z imine. Okay, now how you can draw it? because you have to draw in two ways, right, to get two types of products. So, one way of drawing is that you can keep your RH, because you are talking with your alkene system, O minus, fine, then you can have always your I will add it in here, you have an N plus. You can draw in one way of this same structure. I can draw it and say R H O minus, so same way you can make it so you can make your con and you can make your con rotatory on clockwise, or you can think about making it counterclockwise. If you get counterclockwise, in this case your product will be nitrogen, and you have your R hydrogen with the carbonyl. If you rotate this, so it should be other way around. Okay. So in this case it will be similar systems, but R will be outside, away from you, hydrogen wedged, and this will be dashed, just the opposite one. Fine. So that's really interesting, like how you see when you react your aldehydes with imine. Okay, you can have the possibility of stepwise, where you can do like your con rotatory both the side, clockwise as well as counterclockwise. You can think about both E as well as Z systems. Okay, you get like two types of two products. Okay. So clear with that? So we will see one more reactions which normally happens. Nice example of your Staudinger equations. Third example, where you can have your okay. Now let me know. I will add a triethylamine to this. Okay, what you get? You get a nice ketene. So get a ketene. Okay. Now I can add an imine, okay, to the system. So this will be thermal activation, okay, reaction. So pi 2s plus pi 2a happens in this reaction. So what you get? So it's basically the fixing of the stereochemistry, okay, as we explained in our earlier class. So you end up with a phenyl, you have your carbonyl, you have a lactam, you have an AR, okay, it is AROME. Antibiotic molecule, okay, it's calvolic acid, right? Calvolic acid. You get 92% this product. Very good beta lactam. So, this is a sort of nice reaction for your to a ketene plus imine system. Okay. So, you can do ketene plus alkene and get your cycloketone systems. You can do with your ketene plus imine and you end up with a nice beta lactam system. Okay. The last one example is that which we have already dealt in detail is your ketene with your aldehydes. Nothing there, just like so. You can generate this if you want, like, and then we can take your aldehydes, very commonly done, end up with your beta lactones. Right. There are many other reactions, okay, on ketene chemistry, but these are the important like the reactions which are more concerned with your pi 2s plus pi 2a chemistry. Okay. So, what we did is that we took cycloaddition reactions, then in cycloaddition reactions we took our 2 plus 2 cycloaddition in detail. So, in 2 plus 2 cycloaddition, what we said that 2 plus 2 cycloaddition, if you thermally activate it, you end up with your like basically you cannot do a suprafacial, it is not allowed when you thermally activate, but your suprafacial plus anterofacial is allowed. But one thing to be in mind is that the geometry should be favored. But once we went down for photochemical activation, what we observed? We observed that if you it happens very nicely because it is suprafacially allowed, right, because both geometry both orbitals are favored. So, finally, we drawn the conclusion, if you heat in 2 plus 2, most of the time you will get supra antera geometry allowed, but if you shine light, it is reaction goes very nice and you get a suprafacial one. And we saw some examples on photochemical activation, and we saw that how it is important, like you get a specific products because they are SS. So, supra. So, you get a more specific type of products. Then we took and we saw that normally 2 plus 2 cycloadditions of alkenes, if you heat, never happens because the geometry is not favored. But we went to ketene chemistry, and in ketene chemistry we observed that this pi 2s plus pi 2a happens nicely because we have seen the orbital. Okay. It sits exactly perpendicular to your alkene, and you can have a nice geometry which can favor your pi 2s plus pi 2a. Then we said we will study ketene chemistry. We studied the synthesis of ketene. We saw 4 nice methods of which we can synthesize ketene chemistry. Like we were discussing like alpha chloro, okay, and then we will discuss about esters, and then the alpha chloroacyl chloride system by zinc. Then we said like photochemical and thermal activations of azo can also end up with the synthesis of nice ketenes. Once we synthesize ketenes, then we said we can do some good reactions. We did reactions with olefins. Okay. In olefins, we observed an interesting fact that in Z olefin you will get only one product, but if you go for E olefin you get in 2 different products, and we said that it might go through stepwise mechanism, and we saw that. And then we later on we moved to lactam chemistry. We said that ketene with your imine gives you a nice lactam, and again we got two products, and we understood by Korn rotatory, both one can be clockwise, another can be counterclockwise, and we said that we can have some control across it because it is a clockwise. So, we can have some control based on their substituents. Then finally, we discussed ketene plus aldehyde reactions, and we said that we got beta lactones. Okay, these are overall view about your 2+2 cycloaddition. So, you have some 2+2 which can go in light, you have some 2+2 which can go in heat. Clear? Okay. That's more about your 2+2 cycloaddition reactions. We will see all these pericyclic reactions. What we will do is that at the end we will do lot of problems. We combine all this, like we will combine sigmatropic, we will combine cycloaddition, electrocyclic, then we will do a combined problems, like at least we will try to do 10 or 15 problems and see how we can do it. Okay, fine. So, now we will slowly get into our 4+2 cycloaddition reactions. So, in 4+2 cycloadditions, what we studied is that we studied one system where you have a diene, okay, butadiene with an alkene giving you a cycloproduct. Okay. Another, we have studied an example where you have an A minus P plus double one C with an alkene giving you another cyclic product. Okay. And you can name this reaction as Dilsalder reaction, which we know. Okay. Another is 1,3 dipolar cycloaddition. So, this is what these two reactions we are going to discuss under 4+2 cycloaddition. Okay. So, we will initially we will take Dilsalder reaction, we will try to understand Dilsalder reaction in detail. Once we finish Dilsalder reaction, then we will go for 1,3 dipolar cycloaddition. These are the two reactions which we are going to discuss. So, we will start with Dilsalder reaction. A simple representation, as we saw, it is an butadiene with your alkene on heating. Okay, on heating an alkene R. Yeah. This on heating. Okay. This reaction was first discovered, I think this reaction was first discovered in 1928. Okay, by Potadils and this student. Okay, this student is this student Kurt Alders. Okay. So, 1928 they discovered this Diels, and discovered by Diels and his student Kurt Alders. I think this is the first reaction which is named by the chemist, named, okay, like Dilsalder, because most of that time most of the reactions were named based on the chemistry, not on the based on chemist. I think this is the first reaction which is named based on chemist. Okay, Diels-Alder reaction, and I think in the year 1950, okay, they were given Nobel Prize in chemistry. Okay, this so Diels and his student Alder, 1950, I think they shared Nobel Prize in chemistry, okay, for this discovery. This Diels-Alder. So the mechanism of Diels-Alder reaction is understand the mechanism of Diels-Alder. It's it's like a proper your pericyclic reaction. Okay, very concerted. If you want to write the transition state, it should be very concerted reaction. Okay, goes to transition state and this reaction goes heating very nice. Okay, so what are the substrates you are looking for here is this is your diene, we call them diene, and they carry your 5 pi electron system. This is your dienophile, which carries your 2 pi electron system. Okay. So, since it is a 4 pi and 2 pi interaction, so we call them as a 4 plus 2 cycloaddition. Fine. So, what are the two important steps here to be, three important steps to be noted is that one, we should understand how the diene should be. Okay. Then we should understand the dienophile. Then we slowly will get in and should understand why this reaction prefers to be in heating or based on their FMO theory, and then what happens in light. Okay, whether this that all we should understand in detail. Then we will get into the stereochemistry aspect, whether this reaction, because we know that Diels-Alder reactions are facial selective, their exo-endo selectivity is there, they are regioselective. So, we have all these things. So, we will study that in detail. Okay. First, we will get into diene and see how the diene should be. Yeah? How diene should be in Diels-Alder. Any idea how the diene should be in Diels-Alder? What should be normally dienes? That I am talking about more about the double bond. Okay. Normally the dienes should be electron rich, right? In Diels-Alder, that is the first thing diene should be. Diene should be or dienes are electron rich, or diene should be electron rich for good Diels-Alder reactions to happen. In dienes of, okay, there are mostly two types of dienes which you see in Diels-Alder reaction. Okay, one you see your acyclic dienes. Okay, another you can see your open chain one. Right, one can be a cyclic type of dienes you see lot. Another you see your open chain dienes. Okay. If we will take this open chain diene and we will see what is the best example of your open chain dienes. Your butadiene, right? See, if you take butadiene, just I will write the general formula. Okay, butadiene. How this once you put it in the solution, normally how this exists? You have this you have one on transoid phase and another should be your cisoid phase, right. This always will be in this. Right, but if you see, this is the most geometrically favored, tries to be in this form. But if you want to do Diels-Alder reaction, okay, for Diels-Alder reaction, it can be any diene. That is not the criteria whether it is an open chain diene or it is a cyclic diene or cyclic diene. The criteria is that a diene should be in S-cis configuration. Okay, that is very important to happen a Diels-Alder reaction. So, your diene should be properly in a cis. Okay. It should adapt a cis conformation, that is very important for your Diels-Alder reaction. Like if you have a butadiene, this does not undergo any reaction with your Diels-Alder, okay. But you know that once you heat, they can convert into S-cis form, and then this part undergoes Diels-Alder reaction, okay. So, that is the first condition you should know. So, that happens most of the time in your open chain. Open chain, one advantage you have is that, yeah, you can say limitation or advantage, you can convert your trans to cis by heating or some other means, okay. So, there will be always a equilibrium between these two happening, or you can thermally activate to move one and do the thing. So, you can move to S trans systems. So, that is about your open chain dienes. But if you go to your cyclic dienes, okay, furan, I have systems like cyclopentene, okay. So, see this is your furan, cyclopentadiene and cyclohexane diene, right. See, if you see these guys are properly in their S-cis conformation, okay. They are locked S-cis conformation, basically they are locked in S-cis conformation, and they are a very good excellent dienes for Diels-Alder reactions. They just get locked in their S-cis, so it is a very good dienes for Diels-Alder reaction. But if you take this type of cases, like these are S-cis conformation. These are S trans, okay. If you see, look their structure, they are S trans, they are locked in S trans. So, they cannot do Diels-Alder reaction. A very important part of your diene, okay. So, basically your diene should be your diene should be electron rich, that is your first thing you come into your mind in Diels-Alder reaction. In dienes there can be categorized as two, which is your open system, okay. Another should be your cyclic system. In open system you have this transoid S trans and S cis, which can always move across, and you found that S cis is very good for doing better diene for doing Diels-Alder reaction. So, but in open system you can always move across, okay. But in cyclic system you get a locked system, okay. So, your S cis should be really good for doing Gill-Southern reactions like your furan, cyclopentene, 1,3-cyclohexadiene, all these are very excellent system for Gill-Southern. But you have this Declin type of system which we have written, they are not good for Gill-Southern because they are locked in your S transform. Okay. That is the two important things you remember in diene. Okay. Now, we will get into dienophile. How dienophile should be? Yeah, that is now we know because diene should be electron rich. So, it should be other way around, there should be electron poor. I am talking about the double bond. So, that means what you say, if you have an electron withdrawing group on your dienophile, becomes electron poor and you can do good chemistry, they can be a very good dienophiles. For example, if you take a simple alkene, okay. This is sort of a poor dienophile. Okay. But if you can attach a sort of electron withdrawing, okay, then it becomes a good nucleophile, sorry, a good dienophile. Same way you can think of even attaching your nitrile, very good electron withdrawing groups. Right. So, your diene should be electron in rich and your dienophile should be electron in poor. So, these are the two things about your substrate when you talk about your Gill-Southern reactions. Fine. So, next class what we will do? Next class we will get into and understand how this HOMO-LUMO interaction should be favored for heating and light. Okay, that we will see in Gill-Southern reaction in next class. Fine. So, with this we will today's we end up our class. Okay.